ሰላም እንዴት ናችሁ? ዛሬ በሶስተኛ ጊዜ በወርክሺት ሶሉሽን ተመልሻለሁ። ይህ ወርክሺት የተዘጋጀው ለቤዚክ ማትማቲክስ ፎር ናቹራል ሳይንስ ወይም ደግሞ ማትስ 1011 ለሶስተኛው ቻፕተር ኦን ፋንክሽን ላይ የተዘጋጀ ናቸው። ስለዚህ እነሱን በጋራ እናያለን ማለት ነው። እዚህ በቀጥታ በወደ ጥያቄዎቹ ከመግባቴ በፊት ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ሰዎች ካላችሁ ቻናሉን ሰብስክራይብ እና ይህን ቪዲዮ ላይክ በማድረግ ብትጀምሩ ደስ ይለኛል። ስለዚህ በቀጥታ ወደ ጥያቄዎቹ እንሄዳለን። The first question is this one, that is question number 1. It says consider set A containing elements 1 and 2 and B containing density. Then the first question under this could be list all elements in a cross B. So in order to determine the cross product of these two sets, especially all the elements of the cross product of these two, let us see how we can, or simply how the cross product of two sets is related to that of the number of elements of the two given sets. We know that A cross B is equal to the set containing a B, so that the first coordinate is select from first set A, and second coordinate B is an element of second set B. And therefore, due to this definition, the cross product of these two could be each and every element of the first set, that simply set A, must be paired with every element of second set. Similarly, the second element of the first set must also be paired with each and every element of second set. So that in this case, this one first element of A must be paired with S, so that we have one S which is an element of A cross B. Again, one could be paired with the second element of set B, so that one T could be an element of its cross product, and second element of set A, that is 2 with S and 2 with T, so that this is the Cartesian product of these two sets, A and B. And as you know, or simply as we clearly observe here, the number of elements of this one, that is A cross B, is 4 ordered pairs, and this will have a direct relationship with respect to the number of elements of set A and set B. That is the number of elements of A cross B if A and B are finite set. That means so that the number of elements of A cross B could be a direct product of the number of elements of A and number of elements of set B. The second question under the same consideration could be, well, asked just to list all the relations R from A to B. We know that a relation from R to B is any subset of the cross product of any two sets. You know this. That is, we have this definition first. A relation from A to B is simply any subset of A cross B. Therefore, especially the number of relations, or simply the number of relations that can be constructed from this set A into that of this one, that seems set B is that, since the cardinality of A cross B is equal to number of A times number of B, we have 4. Therefore, the possible subsets of A cross B, which can be considered as a relation from A into that of B, could be to the power of the number of elements of their cross product, which is to the power of 4, which is 16 relations, so that we can have possibly 16 relations that can be constructed from A into B whenever A and B are with two number of elements each. Therefore, we have this one, that simply there are possible subsets. These are possible subsets of A cross B, including this one, that simply implicit, because implicit is also a subset of any set. The third one, that simply see, list all functions functions F from A to B. We know that a function is said to be a function from an unimplicit set A to that of set B, if and only if the domain of the given function, the first set, that's set A, so that they hit the criteria for the given function from A to B to be a function. That means a function that is f, which maps from A to that of B, assigns exactly one element of B to each element of set A. For each element of set A, that means there must not be an element which is left without mapping for the first set that's simply set A. So that based on this criteria or simple definition, for each of 1 and 2, which is an element of A, we choose, or simply we must choose one of these two, either S or T, which is an element of B. So that's the first function could be 1, which is the first element of set A may be paired with S, and the second element that's simply set the 2, which is an element of A, can be paired with the same it's the same element, first element of this one, that is S. They hit the first possibility. It is a function because 1 and 2 may have the same image, but there is no repetition of a domain. The second function could be 1 can be paired with S and 2 can be paired with T. The difference is, in the first case here, 1 and 2 we are having the same image, that is S, but 1 and 2 here have their own unique images. The third one could be 1 can be paired with T and 2 can be paired with S. And lastly, the last one could be 1 can be paired with T and 2 can be paired with T, having the same image like that of S here. Therefore, these are the total number of functions that can be constructed or simply mapped from this A, having these two elements to this set that's simply set B. The second question, we are given this information, that is, we are given set A containing elements W, X, Y, and Z, and B containing these three elements. Each of the following sets is a relation from A to that of B. So we are asked just to determine which ones are functions from A to B. We are given four alternatives here. So what we are asking here is we are asked just to determine whether the given relations here are functions, not only functions, but also they are functions which are from A into that of set B. Just we have to apply the definition that already we have seen in the previous question. So let us start from the first one. We are given this. Then the first relation we are given based on this would be this one, having simply with three elements. So in order to justify, currently this one or simply this relation is a function, because each and every element of the domain of the given function is paired with exactly one unique element. W is paired with 3. There is no any other image other than that of 3 for W. X has 4 and Y is mapped with 5. But we need to justify whether this function is a function from this set that's simply set A into set B. For this relation R to be a function from A into that of B, the domain of this relation needs to be exactly the first set that's simply set A. Therefore, when we measure this one, a function from A to B must have exactly one ordered pair for each element A and element of A. It says for each, for all, that means. So that's when we check this, R is given to be this one, and then W appears, that is the first element of A appears here, which we with a mapping or simply an image 3. X also appears, yes, it appears, and then it could be paired with, it is already paired with 4. Y also appears and paired with 5, but 0 doesn't appear. There is no, that Z doesn't appear here. That means Z doesn't have any image within this relation R. Therefore, the domain of this relation cannot be the set that's simply set A. Therefore, the relation that is R is not a function from A into that of B. Second one, on the same information, we are given the relation that is R containing these four elements. And also we are asked just to determine whether this relation is a function from A into that of B. So when we check this, W appears and paired with 3, of course here. Similarly, X appears and paired with 4. And also Y appears and paired with 5. Also Z appears and paired with 5. And you clearly observe here, the last two elements of this relation R is Y5 and Z5. That means Y and Z have the same images, and W, X, Y, Z. That means the domain is the elements of that of set A. Therefore, from this, each element of A appears exactly once. There is no repetition, or there is no any element of this one that's simply set A, which has more than one image, so that there is a function from A to B. The next one, see, the relation R is given to be this, W3, X3, Y3, and Z3. And we're asked just to justify again this whether this relation is a function from A to B or not. And when you check this, the image, whether each and every element of A has an image within B, W appears and paired with 3, X also appears and paired with 3 again, Y also appears and paired with 3, even Z appears and paired with the same element, that's simply 3. That is, this is many to one function or relation. Therefore, because each element of A appears once, even though they map to the same element, that's simply 3, and the domain of the given relation is set A, so that there is a function or a constant function from set A into set B. The next one, let R is equal to the same function here, and the relation that is R is given to be this one, and we're asked just to justify again this one is whether it's a function from A to B or not. When we check this, W appears and paired with 3, of course. X also appears and paired with 5. Y also appears and paired with 4. Z appears twice, paired with 3 and 4. Z is paired with 3. Z is paired with 4. So that's one of the elements of the domain of this relation, which is the element of A, is paired with more than one element within the elements of set B, which is 3 and data 4, because 3 is different from data 4. So that this is not the property of a function. Therefore, this relation cannot satisfy condition to be a function, so that it is not a function. Okay, question number 3. It is again determining the following relations are functions or not, and we are asking just to state their domain if and range if they are functions or relations generally. So let us see the first one. The first relation we are given here. We know that for the given relation to be a function, each and every element of the domain of the given function must be paired with exactly one element within its range. That means there must not be any element of the domain of the given relation which has more than one image. So that is mathematical definition of a function. So that when we observe here, we know that 1 is paired with 1. There is no any other element or simple image other than 1 for 1. 2 is also paired with 2. 3 is also paired with 4. And 4 is paired with this one, that is 5. So that there is no any element of the first coordinate which has or simply paired with more than one element within the second one. Therefore, this is a function. So this is a function, and the domain and range could be, we know that the domain of every relational function is the set containing all the first coordinates of each of the elements of the given relation, and set containing the second coordinates will be range. So that's here a domain of the given this function will be the set containing 1, 2, 3, and the data 4. And similarly, the sets or simply the outputs or simply the range could be again 1, 2, 4, and this one that is 5. Question number 3C. We are given this relation and we are asked just to just determine whether this relation is a function or not, and we are also asked just to put a domain and range of the function. We know that when we check this, 1 appears twice. 1 is mapped with -2 and 1 is also mapped with +3 here. So that due to the existence of this element, automatically this relation cannot satisfy the condition or cannot be a function. Even though it is not a function, but it is domain could be the set of the first coordinate, that is 1, -2, -1, and 1 here. And the range could be a set containing -2, 0, 2, and 3. -2, 0, 2, and 3. Therefore, the relation is not a function, and its domain is this one. Okay, so the next one, determine if this relation is also a function. That is the same question. So in order to check whether this relation is a function or not, we know that 3 appears twice with 2, and this one that's simply 3, -3 with 2, -3 with 3, that means. And since input -3 has 2 different outputs, 2 and 3, so the relation cannot satisfy the condition to be a function. And the domain is set of the first coordinate, that's -3, as 3 and 5, and its range will be 2, 3, and -5. Then question number 4. We are given a function f of x equal to this quadratic function and g of x to be this linear function, which is x plus 1. Then what we are asked here is we are asked just to find the operation on this one, that is the sum, product, the quotient of f over g and g over f, and the composition f of g of x and g of f of x. So let us see one by one. The first one, that is the sum and the product of these two, we are given that is f of x and g of x here. So that's the sum of these two, that is f plus g of x equal to f of x plus g of x. So when we substitute the values or simply the terms of f of x and g of x in the place of f of x and g of x here, we have 2x squared minus 3 for f of x and x plus 1 for g of x. And if we add them together, since we are adding for the constant terms, we have 2x squared plus x minus 2, which is the sum of these two functions. And the product could be using the same process, f times g of x equal to f of x times g of x, which is equal to 2x squared minus 3 times x plus 1. So that the product of these two could be 2x cubed plus 2x squared minus 3x minus 3. And next, on the same function f of x and g of x, let us see how we can obtain f over g and g over f. We know that f over g of x is equal to f of x over g of x. So that if we substitute f of x, the terms of f of x and g of x, we have 2x squared minus 3 over x plus 1, but this function that is a quotient function will be defined only when the denominator, that's g of x, is non-zero. So that the domain of this function could be the set of real number, except the set real number which can make this one to be zero. In this case, that is x minus 1. so that this is the quotient. Similarly, the quotient of g over f of x could be g of x over f of x, which is equal to x plus 1 over 2x squared minus 3. And the domain of this one could be a set containing set of real number without the real number making the denominator to be 0, but this could be 0 only when either x is plus or minus the square root of 3 over 2. So that the domain of this quotient function could be the set containing all real number without these two elements of positive number, that is plus or minus the square root of 3 over 2. Next, we are given the same function f of x and g of x. We are asked just to find the composition of f composite of g and g composite of f. First, f composite of g of x could be, by definition, it is f of g of x, so that it is f of, but g of x here is this one, that is x plus 1. So we have f of x plus 1. But when we give a function or simply a certain input for f, the output will be twice of the square of the input minus 3. Therefore, this could be the output for x plus 1 within under f could be twice of x plus 1 the whole square minus 3. Then when we further simplify this one, we have twice of the square of this one, that is x squared plus 2x plus 1. We have minus 3. If I distribute this one over here, 2x squared plus 4x plus 2 minus 3, which is equal to 2x squared plus 4x to minus 3, that is minus 1. So that there is the composition of f and g, which is f composite of g whenever f of x is 2x squared minus 3 and g of x is equal to x plus 1. Similarly, g composite of f of x could be g of twice of x squared minus 3, because f of x is 2x squared minus 3, which is equal to the output for g could be the input plus 1. So that it is just 2x squared minus 3 plus 1, which is equal to 2x squared minus 2. That is minus 3 plus 1 is minus 2. So that it is how we can obtain the composition of two functions. Okay, the same question, that question number 5. Again, it is composition, but the function or the relations are given in the set of ordered pairs. The first one, the first relation which we are given here is a set containing 1, 1, 2, 2, and s is 1. We have 3, so let us try to see one by one. The first one is we are asked just to find s composite of r and r composite of s whenever r is this one and s is here. So the first one, that is for s composite of r, by definition we know that S composite of R is the set containing an ordered pair of this one, that is AC. But for this AC to be the element of S composite of R, there must exist B such that AB is an element of R, the first relation, and BC must be an element of, or simply it should be included in S. If this happens, if AB is in R and BC is in S, so that automatically AC must be an element of the composition of S composite of R. Then based on this fact, when we compare and contrast the given elements of S and R here, we have S composite of R. One is an element of R, but one is not within the domain of S here, so that one cannot have any image within S composite of R. Similarly, 2 is an element of the first set here, and 2 is also an element of the domain of S here, so that 2 is mapped with 2 under R, and 2 is mapped with 3 under S, so that 2 must be mapped with 3 under S composite of R. So that's simply 2, 3 could be an element of S or R. And 2 again, 2 again here, 2 is an element of R, that is an element of S, and this implies 2R must be an element of S composite of R. That means 2 could be mapped with 2 itself under R, and these two, which is the image of S, the image of 2A under R, could be a domain for S and map to base 4, so that 2, 4 will be an element of S composite of R. Therefore, the composition that is S composite of R could be an element containing the set containing 2, 3, and 2, 4. The next one, the same type of question, but there might be different elements. We have 2, 3 is an element of S, but 3 is not within the domain of S here, so that 2 cannot have an image on R composite of S. Similarly, 2, 4 is an element of S here, and 4 is not an element of the domain of R here. There is no 4 which is within the domain of this one, so that 2 cannot have any image under R composite of S. Therefore, the composition that is R composite of S is empty set. The next one, that's B for SOR and ROS. Again, whenever R is given to be the set, that's simply this set, and S is this one. So let us see the first one. The composition that is S composite of R, S is here, and R is this one, so that we know that the first case, that's simply for R. We should start from R here. R, that is 1, 2 is an element of R here. 2, 3 is also an element of S here, so that the image of 1 under the composition of S or R could be this one, that is 1, 3. So that 1, 3 must be an element of S or R. Similarly, 1, 2 is an element of R. We have 1, 2 here, and the same element, so that 2, 4 is also an element of S, because 2 is mapped with 2 and that of 3 under S, so that 1, 4 must also be an element of S composite of R. Next, 1, 3, the second element of R here, is an element of R, and 3, 5 is also an element of S, so that 1, 5, the image of the domain of R, that is 1, and the image of 3 under S, which is 5, which is 1, 5 is an element of S composite of R. 4 is an element of R again here. We have 4 within S, within R, and but there is no 4 within S, or 4 is not within the domain of S here, so that this one, that is 2, cannot have an image over here. Lastly, 5, 7 is an element of the relation that is R here, and we have also here 7, 1 is an element of S, so that 5, 1 must be an element of S composite of R. Therefore, the elements of S composite of R could be 1, 3, 1, 4, 1, 5, and 5, 1. The next one, that is question number 5. See again, S composite of R and R composite of F when R and that of S are given in formula. Then the first one, that is for S composite of R, we are given R to be YR, that is the image of under R could be 1 over X minus 1, and S, say that the image of Y under S could be X over X minus 1. Then the composition of these two, that is S composite of R, could be Y is equal to S of R of X, which is equal to S of 1 over X minus 1, because R of X is 1 over X minus 1. So that this could be further simplified to 1 over, because here it is 1 over X minus 1 is our X over X minus 2 with a property of this one, that's simply S, so that when we give 1 over X minus 1 for S, the output could be 1 over X minus 1, that is the input, over the input minus 2. The input over the input minus 2. So that when we further simplify this expression, we have 1 over 1 minus twice of X minus 1. That is, if we subtract 2 from 1 over X minus 1, we have this one, and which is equivalent to 1 over 3 minus 2X. Therefore, the domain of this one, that is with the domain x different from that of 1 for r, and 1 over x minus 1, which is different from that of 2, which implies x is different from that of 3 over 2 for the composition function, which is s composite of r. Similarly, the other, that is for r composite of r, r is given to be this, and s is this one, so that r composite of s could be y is equal to r of s of x, which is r of s of x is x over x minus 1, so that it is r of x over x minus 2. Sorry. Then the heat equivalent with 1 over x over x minus 2 minus 1, which is equal to 1 over x minus 2 over x minus 2, which can be further simplified to x minus 2 over 2. That means taking or simply multiplying the reciprocal. Already x minus x is 0, minus of minus 2 is positive 2, and this could be taken into the denominator term, so that it could be x minus 2 over 2. Therefore, the domain could be x different from 2 for s, because s is here, that is x over x plus x minus 2, so that it becomes undefined at x equal to, so that that is why we should exclude 2 from being an element of the domain of this function. And for x over x and different from that of 1, always true for x different from that of 2. Then the s composite of r could be y is equal to 1 over s minus 2x for x different from that of 1 and 3 over 2, and r composite of s could be y is equal to x minus 2 over 2 whenever x different from that of will be the summary. The next one, that's question number 6. Again, on compulsion function, but we are given these 3 questions, and let us see them one by one. The first one, that is a, is given to be, we are asked just to find g of x if f composite of g of x is x squared plus 3x, and one of these two, that is f of x, given to be x plus 5. We are given the compulsion function x squared plus 3x, and one of the function, that is this one, that the outer function f of x, given to be x plus 5. So we are asked just to find g of x. So we have, using the definition of compulsion function, f composite of g of x is equal to f of g of x, which is equal to x squared plus 2x, which we are given here. But the output for f could be the input plus 5, so that it could be just g of x plus 5. Since f of x is equal to x plus 5, then f of g of x is equal to g of x plus 5. But this is equivalent with x squared plus 3x. So that from this, g of x could be, if I take this one, that's 5 to the right of the equality, we have g of x equal to x squared plus 3x minus 5. Therefore, we can check this one, that is f of g of x is equal to, I must give us this one, that's x squared plus 3x. Therefore, f of g of x could be x squared plus 3x minus 5 plus 5. Then minus 5 plus 5 is already 0, so that becomes x squared plus 3x. Therefore, perfectly, g of x could be x squared plus 3x minus 5 whenever f composite of g of x is equal to x squared plus 3x, and f of x equal to x plus 5. Next, the second one, question number B. We are given f of x equal to e the power of the square root of x, and we are asked just to find g of x, so that f composite of g of x equal to g composite of f of x equal to x. We know that whenever g composite of f of x equal to x, so that the relationship that exists in between g and that of f is that one is the inverse of the other. One could be the inverse of the other. That means g is the inverse of f, or f must be the inverse of g whenever this condition is satisfied. we need g such that f of g of x equal to x and g of f of x equal to x. This means g is equal to f inverse, the inverse function. So that let's find f inverse. In order to find f inverse, let us start by letting y is equal to e the power of the square root of x. So the inverse of this one could be taking the natural logarithm of both sides of this equation. We have ln y is equal to ln of e the power of the square root of x, which is the square root of x. Then squaring both sides, we have the square of ln y is equal to the square root of the radical x, which is x. So that when we try to solve for x is equal to ln y square. Then in interchanging x and that of y, we have f inverse of x, or simply g of x equal to ln x the whole square for x greater than 0. For x greater than 0. So that this is what g of x is. If we unit just to check whether this one is exactly or perfectly the expression for g of x or not, f of g of x needs to be f composite of g of x were given here, that is x. So f of g of x equal to e the power of the square root of ln x square. The square can be cancelled and become the absolute value of x. The absolute value of x could be, because x is greater than 0 here, e the power of ln x could be x for every x greater than 0. So it is perfectly the function what we need. The next one, that is question number C, that is 6C. Find g composite of h of x whenever g of x is this square root function, that square root of x minus 1, and h of x is x squared plus 1. We know that by definition, g composite of h of x equal to g of h of x, which is equal to g of x squared plus 1, because h of x is x squared plus 1. But the property of this one, that is g, could be whenever we give x for g, the output is always the square root of the input minus 1. So that g of x squared minus 1 could be the square root of x squared plus 1 minus 1. Further, the simplified form of this one could be the square root of x squared, and the square root of x squared is already the absolute value of x. Therefore, the domain could be h of x is x squared plus 1, which is greater than or equal to 1 for all x. So g of h of x will be defined for all x. It could be defined for all x. That's the absolute value of x, that means. Question number 7 is about these 5 questions, which we are asked just to find, or simply just to justify whether the given relations from functions from R to R are 1 to 1 or on to. So let us see them one by one. First one is determine if f of x equal to 6x minus 1 is 1 to 1 and or on to. We know that a function f is said to be 1 to 1 if and only if f of a is equal to f of b implies a is equal to b. That means a function is said to be 1 to 1 whenever no two elements of the domain of the given function have the same image within the corresponding range. Therefore, in order to check whether this function, that is f of x equal to 6x minus 1 is equal to 6x minus 1 is 1 to 1 or not, let's assume that f of a is equal to f of b. If we can able to obtain that a is equal to b, so that the function is 1 to 1. But we know that f of a is equal to 6a minus 1, which is equal to f of b, which is 6b minus 1. So that we have 6b is equal to 6b. If we divide both sides by 6, we have a is equal to b. Therefore, for any arbitrary end b, if f of a is equal to f of b, automatically is equal to b, so that the function is 1 to 1. Similarly, for ontoness, for every function that is for every y, which is an element of R, that is the domain, that means if there exists at least 1x, which is an element of R, with f of x equal to y, so that the function is said to be an odd function. So that based on this, in order to check the ontoness of this function, let's try to solve for y first. We know that y is equal to 6x minus 1. Then if we try to solve for x, we have x equal to y plus 1. So that for each and every element of this one, that is y, which is an element of R, we can obtain at least 1x, which is the pre-image of this one, that is y, so for which is for y. Therefore, the function is unknown. Therefore, the function that is f of x equal to x minus 1 is both 1-to-1 and onto. That's bijective or 1-to-1 correspondence. Second function is f of x equal to x squared plus 1. And we're asking just to justify whether this function is 1-to-1 and or onto function. Let us see the 1-to-1 first. We know that f of 1 is equal to 8. F of minus 1 is also 8. So that two elements of the domain of this function, that is 1 and minus 1, are paired with the same image, that's simply 8. So that this function cannot be an onto function, because since 1 is different from that of 1. So it is not 1-to-1. In order to check its ontoness, we have f of 0 is equal to 7 is the minimum value of this parabola, which opens in the upward direction. So that f of x is greater than or equal to 7 for all x. Thus, for y less than 7, example, y, if we take y is equal to 0, because the function is from R to R, there is no nx which exists as f of x equal to this one, that's simply 0, so that the function is not onto. Therefore, the function f of x equal to x squared plus 1 is neither 1-to-1 nor onto. The next one, that's simply see, we have the function f of x equal to x cubed. Now that this function is an increasing function. So that whenever a function is a strictly a function, increasing function, it is expected to be 1-to-1 function. Anyways, let us see. It is 1-to-1 by following the definition. Let f of a is equal to f of b. This implies a cubed is equal to b cubed. Then taking the cube root of both sides of this equation, we have a is equal to b. Therefore, for f of a is equal to f of b, we can have a is equal to b. Therefore, the function is 1-to-1. Yeah, we know that cubic polynomial is strictly increasing, so that every strictly increasing functions are onto function, I mean 1-to-1 functions. In order to check it as 1-to-1, I mean ontoness, let us try to solve for x first. For y, for any y element of R, we have x equal to the cube root of y, so that for any y, we can obtain the corresponding value of x, which could be considered as a pre-image for this y. Therefore, the function is an onto function, because for each and every element of the range of the given function, there exists at least one pre-image within its domain, so that it is 1-to-1. Therefore, the function f of x equal to x cubed is both 1-to-1 and onto, so that it is bijective or 1-to-1 correspondence. The next one, determine f of x equal to 2x plus 1 over x minus 7 is 1-to-1 and or onto. Let us see 1-to-1 as first. We know that the domain is set containing a set of real number without 7, because it's undefined at 7 here. The codomain is R, since it is from R to R, just we are informed at the beginning. Then, in order to check 1-to-1ness, suppose f of a is equal to f of b, so that f of a would be twice of a plus 1 over a minus b, and f of b is to be plus 1 over b minus 7. So when we further simplify this one, if you multiply this one, that's crisscross, we have to be a plus 1 times b minus 7, this is equal to this. Then further simplifying this one, we have twice of AB minus 4B plus B minus 7 is equal to twice of AB minus 14B plus A minus 7. Here we have this one, that is this thing can be cancelled by this one, that is twice of AB, twice of AB. We have 7 again here. This 7 can be cancelled by this one. Again, we have minus 14b minus 14a plus b minus 14b plus a. So when we have this one, that means cancellation. We are given this one minus 14a plus b is equal to minus 14b plus a. And rearranging these terms, we have b plus 14b is equal to a plus 14a. That means taking this one to the right side and bringing this one to the left gives this one, and this implies 15b is equal to 15a. Dividing both sides by 15, we have a is equal to b, so that the function is one-to-one function. For unknown to us, a horizontal asymptote y is equal to 2. That means the horizontal asymptote, this is a rational function with the same degree for the numerator and the denominator, so that when the numerator and denominator of the given function are equal, so that the quotient of the coefficients, the leading coefficients of the two functions could be taken as the horizontal asymptote for the graph of the given function. That is why y is equal to 2, which is y is equal to 2 over 1, because the coefficient of the numerator is 2 and the coefficient of the denominator is 1, so that 2 over 1 or 2 could be the horizontal asymptote. So this divide coefficient is this, so f of x never equals to 2. It never, to be exactly, is equal to 2, because y is equal to 2 is a horizontal asymptote. The graph may approaches, but it never touches or simply intersects, so that there exists within the range of this function, there is 2, which is an element of the range of the given function, without any image, so that the function is not an unknown function. Okay, the next one could be question number 8, which is finding the inverse of the given function. So let us start from the first one. The first one could be find the inverse of h of x equal to the cube root of x minus 3. So in order to follow or simply just to have the inverse of the given function, we have usual steps or simple around 3 or 4 steps. The first step will be letting f of x